In this lecture, we'll talk about properties of functions. First, we'll talk about even functions and odd functions. By definition, an even function has a graph that exhibits symmetry with respect to the y-axis, and the function value of negative x is equal to the function value of x. And an odd function has a graph that exhibits symmetry with respect to the origin, and f of negative x is equal to minus f of x. So using the previous definitions, we want to determine whether or not functions are even or odd using their graphs. Let's do a couple of examples. So using the following graphs, determine if the corresponding functions are even, odd, or neither even nor odd. So here's our first graph. To determine if the function is even or odd, we need to identify what symmetry the graph may have. So if we look at this graph, does it have symmetry with respect to the y-axis, or symmetry with respect to the origin, or no symmetry at all? Since the portion of the graph to the right of the y-axis is a mirror image of that to the left of the y-axis, this has symmetry with respect to the y-axis. And so since it has symmetry with respect to the y-axis, the function is even. What about the function whose graph is shown here? Is it even, odd, or neither? Again, to determine whether the function is even or odd, we need to look at the symmetry. Now, this graph does not exhibit any symmetry, so the function is neither even nor odd. Let's look at one final graph. Is the function represented here even, odd, or neither? So again, we need to determine the symmetry of the graph. And this graph exhibits symmetry with respect to the origin. That is, if we took it and rotated it 180 degrees, the graph is the same. So this has symmetry with respect to the origin, which means that the function is odd. We don't necessarily need the graph in order to identify an even or odd function. We can do it algebraically as well. To determine whether a function is even, odd, or neither algebraically, what we want to do is replace x within the function with minus x. If the resulting function is the same function that we started with, then the function is even. If the resulting expression is the exact opposite, that means each term changes signs, positive to negative, of the function that we started with, then the function will be odd. Let's look at a few examples. Determine algebraically if the following functions are even, odd, or neither. We have f of x equals 2x to the fourth minus x squared, f of x equals 3x cubed plus 5, and f of x equals 2x to the fifth plus x. Let's start with f of x equals 2x to the fourth minus x squared. To determine if the function is even, odd, or neither, we're going to replace x with minus x. So we have f of minus x equals 2 times minus x to the fourth minus a negative x squared. If we simplify that, negative x to the fourth is just x to the fourth, and negative x squared is x squared. So f of minus x is equal to 2x to the fourth minus x squared, which is the same as the f of x that we started with. So this function is even. Let's look at f of x equals 3x cubed plus 5. Again, to determine if it's even, odd, or neither, we replace x with minus x. So we have f of minus x equals 3 times minus x cubed plus 5. If we simplify, f of minus x would equal 3 times negative x cubed plus 5, which gives us f of minus x equals negative 3x cubed plus 5. And this result is not the function we began with, and it's also not the exact opposite of what we began with, so this function is neither even nor odd. For our last example, we'll look at 2x to the fifth plus x. So again, we start by replacing x with minus x. So f of minus x equals 2 times minus x to the fifth plus a minus x. If we simplify, we get f of negative x equals negative 2 times x to the fifth minus x. We can pull a negative out of both terms, so f of minus x equals negative 2x to the fifth plus x. And so f of minus x equals the exact opposite of our original function f of x, which means the function 2x to the fifth plus x is an odd function. Next, let's talk about increasing, decreasing, and constant functions. By definition, a function f is increasing on an interval I if, for any choice of x1 and x2 in I, with x1 less than x2, we have f of x1 is less than f of x2. And what this means is that the graph of an increasing function goes upward from left to right. All right, next, by definition, a function f is decreasing on an interval I if for any choice of x1 and x2 in I, with x1 less than x2, we have f of x1 is greater than f of x2. This means that the graph of a decreasing function will go downward when examined from left to right. And finally, by definition, a function f is constant on an interval I if for any choice of x1 and x2 in I, with x1 less than x2, we have f of x1 equals f of x2. This means that the graph of a constant function is a horizontal line. Let's look at a couple of examples. First, let's consider the graph of the function presented here. Looking at the graph, we should be able to determine on what intervals is the function increasing. So, from left to right, in which intervals or what values of x is the graph moving upward? So starting at the point -1, 0 and going to 0, 2, the graph is rising upward. When we talk about intervals, we're only talking about x values, so between x equals -1 and x equals 0, our function is increasing. So we'll have the interval -1, 0, and we use open parentheses because -1 and 0 are not included. We also see that the function is increasing on the far right-hand side of the graph, between x equals 1 and x equals 3, so we'll add the interval from 1 to 3 to the intervals on which the function is increasing. So our function is increasing on the intervals from -1 to 0 and from 1 to 3. Next, we want to determine on what intervals the function is decreasing. So where is the graph going downward from left to right? So the far left-hand side of the graph, between x equals -3 and x equals -1, the graph is going downward. So this means that the graph is decreasing from x equals -3 to -1, which we'll write in interval notation. And the graph is also going downward or decreasing between x equals 0 and 1. So the intervals on which the graph is decreasing are -3 to -1, and from 0 to 1. Lastly, we want to determine on what interval is the function constant. So where does the graph have a horizontal line? And for this graph, there are no horizontal portions, so the interval where the function is constant is none. There is no interval where the function is constant. Here's another example. Consider this graph, and again, we want to determine on what intervals is the function increasing, on what interval is the function decreasing, and on what interval is the function constant. Take a couple minutes and see if you can figure this out yourself, and when you're ready to continue the slideshow, we'll go over it together. So let's start with the increasing parts. The graph is increasing between the points -3, -2, and -2, 1, and it's also increasing between the points 0, 1, and 2, 2. Well, remember, we form our intervals using only the x values, so the function is increasing on the intervals from -3 to -2, and from 0 to 2. Next, we want to determine where the function is decreasing, so the graph is going downward between the points 2, 2 and 3, 0. Using just the x values, this gives us the interval between 2 and 3. And then finally, to find out where the function is constant, we look for a horizontal line, and our graph has a horizontal line between the points -2, 1 and 0, 1. So our function is constant on the interval from -2 to 0. Next, we want to talk about finding local minima and maxima using a graph. By definition, a function f has a local maximum at the point x equals c if there's an open interval I containing c such that for all x not equal to c in the interval, f of x is less than f of c. Basically, what this definition means is that a local maximum will occur at any point on the graph that is bigger or higher than all of its neighbors on either side. And by definition, a function f has a local minimum at x equals c if there's an open interval I containing c such that for all x not equal to c in the interval, f of x is greater than f of c. And basically this means that a local minimum occurs at any point on the graph that is smaller or lower than all of its neighbors on either side. So let's look at an example. Consider the graph given here. We want to find the local minima and local maxima. So first, we want to find the local minima for this graph, if any exist. Remember, a minimum value will occur at any point that is lower than all of its neighbors. So if we look at this graph, there are two such points. The point -1, 0 is smaller or lower than neighbors on both sides, and the point 1, 0 is also smaller or lower than its neighbors on both sides. So our local minima are the points -1, 0 and 1, 0. Next, let's think about local maxima for the graph. So remember, a local maxima will occur at any point that is higher than the points around it. And we have one such point that's higher than the points around it. That is the point 0, 2. So a local maximum will occur at 0, 2. To finish off this lecture, we want to talk about average rate of change. So if a and b, where a is not equal to b, are in the domain of a function y equals f of x, then the average rate of change of f from a to b is defined as follows. The average rate of change is the change in y over the change in x, so that's f of b minus f of a divided by b minus a, again with a not equal to b. The average rate of change of a function from point a to b is related to the secant line that intersects the function at a and b. So the average rate of change of the function from a to b is the slope of the secant line containing the points a f of a and b f of b. So if we consider the graph of this function with points a f of a and b f of b, the secant line is the line that goes through those 2 points, and the slope of that line will be the average rate of change of f from a to b. Let's work a couple of examples where we'll use rate of change. So consider the function h of x equals -2x squared plus x. Find the average rate of change of function h from 0 to 3. To find the average rate of change from 0 to 3, we first need to find the function values at 0 and 3. So let's consider h of 3. If we plug 3 in for x, that gives us -2 times 3 squared plus 3, which we can simplify to give us -2 times 9 plus 3. -2 times 9 is -18, so we have -18 plus 3, which is -15. So the function value h of 3 is -15. Similarly, if we plug in 0 for x to find h of 0, we get -2 times 0 squared plus 0, which simplifies to be 0. So the function value h of 0 equals 0. Now that we know h of 3 and h of 0, we can plug them into the formula for rate of change. Remember, average rate of change equals the change of y divided by the change of x, so that will be h of 3 minus h of 0 divided by 3 minus 0. If we plug in the values that we've already found, h of 3 was -15 and h of 0 is 0, so we have -15 minus 0 divided by 3 minus 0, which simplifies to be -15 divided by 3, which is -5. So the average rate of change of h from 0 to 3 is -5. Continuing our example, since we found the average rate of change from 0 to 3, we can now find the equation of the secant line that goes from 0 to 3. So from the first part of the example, we know that the 2 points on the line are 3, -15, and 0, 0. And we know that the slope of the line is going to be -3 because that was the average rate of change. So we can use the point slope formula for a line, y minus y1 equals m times x minus x1. And we can use either point, 3, -15, or 0, 0. For simplicity, I'll use the point 0, 0, so y minus 0 equals -3 times x minus 0. And if we simplify that, we get y equals -3x.